Section 5.4, Indefinite Integrals. This section is actually quite simple. We're simply using the integral ideas we've seen over the past couple of sections to create a family of antiderivatives for a function lowercase f. We can now think of those family of antiderivatives as just simply the integral of f of x dx. Notice here there are no limits on the integration symbol, so this is why we call it an indefinite integral. There are no definite limits. So thus, when we write the indefinite integral of lowercase f of x dx equal capital F of x, this means the same thing as capital F prime of x is equal to f of x. This is the exact same thing that we saw in section 4.9 on antiderivatives, but now we're just adding this notation of an indefinite integral. So these are really just antiderivatives. So right below I have a whole table of typical antiderivatives which are directly related to the derivatives we saw earlier in the class. So all the way back in chapter 2, we started learning about derivatives, and there you have them on the left. So we've got constants, power, natural log, exponential, trigonometric, and then inverse trigonometric functions. This is just an example of a whole bunch of things that we've seen. And on the right, you have the related antiderivative. Essentially, on the left, you have one direction, take a derivative. On the right, you have the opposite direction, take the antiderivative. Notice on all of these antiderivatives we have on the right, there are the constants capital C throughout. This is again a reminder of in section 4.9, when we had a general antiderivative, we had to have this constant capital C. So there they are organized for you to refer to at any time. Feel free to take a screenshot of this list. You can find this. I just Googled this. I just brought it into the lesson, so you can easily find that on your own. But it is definitely something that you want to memorize. You're going to be using these things so much in Math 70, Calculus 2. This is not something where you want to keep looking back at a table. It just becomes a lot easier if you know them off of the top of your head. We will also keep in mind that from that list, some of the antiderivatives we find will only be valid on a certain interval. So for example, if we write the indefinite integral of 1 over x squared dx is equal to negative 1 over x plus c, just using an antiderivative, we understand that this means it's only valid on a certain interval. In this case, we can't have x equal to 0, so we'll just assume that we understand that that's true. The whole point is that we're getting a function. We understand that there are concerns about domain, but if we don't have any definite values for our integral, then we're just creating a function, that's all, with its own implied domain as well. Notice that we'll also be writing capital C with our antiderivatives, again because we're finding a general antiderivative, and what that C is called is a constant of integration. So you're going to be hearing me say that a whole bunch, and especially in Math 70, you'll hear that again. Constant of integration, we're always going to need that if we have an indefinite integral. So here's an example. Evaluate the indefinite integral of cosine theta divided by sine squared theta. And I forgot the differential notation, but if you notice the variable here is theta, so I have to be integrating with respect to theta. So this should say cosine theta divided by sine squared theta d theta. I'm integrating with respect to theta. So now, just because I'm using theta doesn't mean it doesn't apply to anything that's up in the table above, which had x. Again, these are just variables. They can be any symbol that they want. But I will note that I don't have anything that has cosine of a variable divided by sine squared of a variable. That doesn't show up. So what we're going to start to have to get used to is we can't possibly memorize all of them, so we're going to have to use other things at our disposal to try to evaluate these integrals. So we're going to simplify, and we're going to use some trig identities. This is going to take some practice. This becomes really the main point of Calculus 2 is practicing integration. So I'm going to start with what we have, the integral of cosine theta divided by sine squared theta d theta. And I'm going to simplify by actually splitting up the fraction that I have there. So instead of cosine theta divided by sine squared theta, I'm going to say cosine theta divided by sine theta times sine theta d theta. And this is the same thing as in the integrand, the fraction 1 over sine theta times cosine theta divided by sine theta d theta. And now here's where the identities will come in. 1 over sine theta is the same thing as cosecant theta. Cosine theta divided by sine theta is the same thing as cotangent theta. And so now let's go back to our list, and we'll recognize that this is related to where we had the integral of cosecant x cotangent x dx. So that's just the antiderivative of cosecant x times cotangent x, which relates to the derivative of cosecant x is negative cosecant x cotangent x. So this antiderivative is just negative cosecant theta, because that's my variable in this context, and then plus capital C, my constant of integration. So a lot of what you start to see in integration comes down to simplifying your integrand first, trying to rewrite it, and then using some of those basic antiderivatives to move on to the end. So here's another example. Now this is a definite integral because there are limits of integration. So now everything's just going to be thrown in all together. You will be seeing many examples of evaluate this integral, evaluate that one, and some of them will be definite and some of them will be indefinite. So I still need to use my antiderivatives to even get to an answer, as we saw in the previous section with the fundamental theorem of calculus. So I need to simplify the integrand. That's our first step. So I'm going to write the integral from 1 to 9 of what we have in the integrand to begin with, 2t squared plus t squared times the square root of t minus 1 divided by t squared. And then I'm integrating with respect to t this time. Now I understand that you're tempted to start crossing out t squareds, but you are now reaching the end of Calculus 1. We should know now that you are not allowed to just do that whenever you want. You are allowed to split up a fraction if you have just a monomial in the denominator. So since I just have t squared, I can rewrite the integrand as a sum of fractions. I can take 2t squared and write it over t squared. And then plus t squared times the square root of t divided by t squared. And then minus 1 divided by t squared. You are allowed to do that. So now in each fraction, we can cancel things out. There's a common factor of t squared in the first fraction. There's a common factor of t squared in the second. And what you have in the third fraction, there isn't anything to cancel, so it just is 1 over t squared. So this gives me the integral from 1 to 9 of the constant 2 plus the square root of t minus 1 over t squared dt. So now let's go back to our list. For the number 2, that relates to a constant. The integral of a constant is just going to be that constant times the independent variable. So in our case, in our example, it will be t. When you start looking at some of the other ones, you might notice that you don't see anything with a radical or where you've got 1 over t squared, but you should notice that you do have things involving powers. So if you have something other than 1 over t, you have to use the power rule. So it's the power rule of derivatives, but now we're just using it in reverse with antiderivatives. So both of these we would like to write as a power function. So before I use any antiderivatives, I'm just going to rewrite one more time the integral from 1 to 9 of 2 plus The square root of t we've seen many times before is t to the 1/2 power. And then 1 over t squared is the same thing as t to the negative 2 power. And then dt. So now here's where we use our antiderivatives. So first of all, the antiderivative of 2 would just be 2t. So I'll make a note that 2t, that's just the antiderivative of 2. And then t to the 1/2, remember what we saw in earlier sections, I'm going to increase my power, so 1/2 by 1. 1/2 plus 1 is 3/2. And then I have to divide by that new power. So this would mean dividing by 3 over 2. But dividing by the fraction 3 over 2 is the same thing as multiplying by the reciprocal, 2/3. So this is just 2/3 t to the 3/2. And then with my last expression, t to the negative 2, I have to again increase the power by 1. So negative 2 plus 1 is negative 1. And then I have to divide by the new power. So let's notate these. 2/3 t to the 3/2 is the antiderivative of t to the 1/2. And then t to the negative 1 divided by negative 1, that's the antiderivative of t to the negative 2. So now we're not going to need a constant of integration because I have a definite integral. So here's some new notation for that. To remind ourselves that we need to evaluate at our limits after we use these antiderivatives, I'm going to write something like this. It's a square bracket at the end where I have a 1 in the bottom and a 9 in the top. So my upper limit of integration is 9 and my lower limit of integration is 1. That's just a notational device to remind ourselves to evaluate at our limits of integration. So what this means is I'm not quite done yet. Here's where we use the fundamental theorem of calculus part 2. I'm going to have everything that I had after taking the antiderivatives and evaluate at 9. So this will be 2 times 9 plus 2/3 times 9 to the 3/2 minus 9 to the negative 1 divided by negative 1. But because I've got those negative 1s hanging around, this will just be plus 9 to the negative 1 power, which is really just 1/9. So that's evaluating at my upper limit of integration. And then we have to also plug in our lower limit of integration. That's separated by a subtraction. I'm using parentheses to organize. The first set of parentheses is my antiderivative evaluated at 9. And the second set of parentheses is my antiderivative evaluated at 1. So then I have 2 times 1 plus 2/3 times 1 to the 3/2 power, and then plus 1 to the negative 1. And now let's simplify what I have remaining. 2 times 9 is 18. 9 to the 3/2, that's the square root of 9, which is 3, cubed. So 3 cubed is 27, so this becomes plus 2/3 times 27, which we'll be able to simplify a little bit with that. And then plus 9 to the negative 1 is just 1/9. And then I need to distribute my negative, minus 2 times 1, so that's minus 2. Minus 2/3 times 1, so that's minus 2/3. And then minus 1. So now we can just get a final answer from those. So 18 plus 2/3 times 27, that's 2 times 9, so that's another 18, so I've got 36. Minus 2 minus 1, so that's 33. Combining all of our whole numbers. And then plus 1/9 but then minus 2/3, which is minus 6/9. So this turns into minus 5/9. So that's 32 and 4/9. So notice this is similar to doing an indefinite integral, but because of the limits of integration, I don't have a constant of integration, and I am going to get a single numerical answer at the end. So then one main application of the fundamental theorem of calculus that we saw is with what we call net change. We had discussed this before when we were relating velocity to position. So here's a theorem. The integral of a rate of change is the net change. So in this case, the integral from a to b of capital F prime of x dx is equal to capital F of b minus capital F of a. This makes sense if we just remember that f prime of x represents the rate of change of the function y equal capital F of x with respect to the independent variable x. Also, we need to remember that f of b minus f of a, that is just simply the change in y when x changes from a to b. So although y can take on a whole bunch of values between a and b, and sorry, that should say f of a and f of b. So while the function y can vary all over the place, the thing at the end, capital F of b minus capital F of a, that's just the net change from where it began to where it ended, no matter what happened in between. So first, a couple of other contexts that we may have seen in other aspects. If capital V of t is the volume of water in a tank at time t, then its derivative, capital V prime of t, is the rate at which water flows into the tank. You could also say the same thing if water is flowing out of the tank. Thus, the integral from a to b of v prime of t dt is equal to capital V of b minus capital V of a, which is simply the change in the amount of water in the tank between the two time periods a and b. We've also seen something related to what we've called marginal cost. If capital C of x is the cost of producing x units of a commodity, then the marginal cost is capital C prime of x. So the integral from a to b of capital C prime of x dx is equal to capital C of b minus capital C of a. And that is the increase in cost when production is increased from a units to b units. And then another interpretation of the net change theorem, if the acceleration of an object is a of t equal to lowercase v prime of t, then if we integrate the acceleration function with the limits of integration from a to b, then that's just equal to the velocity at b minus the velocity at a. And this represents the net change of velocity from time a to time b. So let's look at an example similar to something that we've seen before with velocity and position. But what I like about this example is it's going to make sense of something that I said up here. Although we can see some variation, the net change just shows us what happened from beginning to end. So in this example, we're going to let lowercase v of t equal t squared minus 2t minus 3 be the velocity function for a particle moving along a line. For the time period from t equals 0 to t equals 3, let's find these two things. Part A, the displacement of the particle during the time period, and then part B, the total distance traveled by the particle during the time period. So there is a distinct difference between these two things. So first of all, let's note the displacement is just the net change of position. So we started here at time 0 and we ended up there at time 3. How far away are those 2 points? That is just the integral of the velocity function. So to answer part A, we are just going to evaluate the integral from 0 to 3 of v of t dt. However, to find part B, the distance that is traveled, we need to figure out the intervals where the velocity is positive and where it is negative. Because if this particle is moving along a line, it could be going forward and then backward during the time interval. So if you're on the same line, you can't quite tell, but I'm just going back and forth on the same line. So to understand the difference between these two things, imagine you started here at time 0, and then you went away from that point, but then you went back. So at time 0 and time 3, you're actually at the same location. In the grand scheme of things, how far did you travel? Well, you didn't go anywhere, so your displacement was 0, but you did travel during that time. So that's the difference between those two things. The distance that is traveled may be different than the displacement. So how do we answer this question about distance traveled? We use the total absolute value of the area to find the total distance traveled, because if the velocity could be positive or negative, we might have the graph above the x-axis, or in this case the t-axis, and it might be below the t-axis. So we need to take the absolute value of those areas so that they are all positive, and then we can add them up to get a total absolute value of the area. So this means we need to take the absolute value of the velocity function in the integrand. So in this case, distance traveled is the same integral from 0 to 3, but now it is of the absolute value of v of t. So when we get to part B, we'll take a look at that. So let's start with part A, the simpler one of these two. We need to just evaluate the integral from 0 to 3 of our velocity function, which is t squared minus 2t minus 3, and then this is with respect to t. These are just using the power rule again, so for t squared, I would increase the power by 1, 2 plus 1 is 3, and then divide by the new power. For 2t, the 2 carries on through as a constant. T to the first changes to t to the second, and I have to divide by the new power. And then minus 3, which is a constant, that would be minus 3t as the antiderivative, and then I need to evaluate at 0 and 3. And remember, the top limit 3 has to happen first, and then the bottom limit 0 has to happen second. So then this becomes evaluating at 3 cubed divided by 3, minus, the 2's are going to cancel here, so we don't need to copy those down. So then this becomes t squared, or 3 squared, so minus 3 squared, and then minus 3 times 3, and then I'll have, with plugging in the second limit of integration, this will be 0 over 3, so 0 minus 0 squared, which is 0, and then minus 3 times 0, which is 0. So then what I get, 3 cubed divided by 3 is 9, minus 3 squared, which is 9, and then minus 3 times 3, which is another 9, and then minus 0, so we don't need those. So this gives me negative 9. So the distance traveled is negative 9. So what does that mean? If we went forward and backward, at the end of the day, we essentially just traveled 9 units backwards. So now, let's see how much traveling was going on that whole time. So let's find out first where v of t is positive or negative in the interval from 0 to 3. There's many ways that you can do this. We can go all the way back and think, well, we could take the derivative and find out where that's positive or negative, and that might give me some idea of increasing or decreasing. We could find antiderivatives. Really, this is just a simple quadratic function. So how about we just look at some factors? So t squared minus 2t minus 3 is the same thing as t minus 3 times t plus 1. So first of all, v of t is equal to 0 when t is equal to negative 1 and when t is equal to 3. So this is giving you a little bit of a clue as to where this quadratic is equal to 0. And then since this quadratic is opening up, this is giving you another clue as to where the function would be positive or negative. So we're going to consider our zeros of -1 and 3. And I'm just going to use some test points. You could probably already see where this is going. But when I plug in those test points into my velocity function, -2 plugged into t squared minus 2t minus 3, that gives me 4 plus 4 minus 3. That's going to be a positive. When I plug in 0, I get a negative. And then when I plug in 4, I get a positive. So in fact, the velocity function is negative everywhere between 0 and 3. So v of t is less than 0 for t between 0 and 3. So what that means is, if I need to find the absolute value of v of t in that interval, this is going back to an old understanding of how we calculate the absolute value. If a function is negative, then the absolute value of that function has to be the negation of that function. So this turns into negative of the whole function, which then just becomes negative t squared plus 2t plus 3. And to see why this works, take that same test point of 0 that we just talked about. What happens when I plug in 0 now into the absolute value? I get a positive 3. So it does exactly what we need it to do. So for the answer for part B, we need to find the integral from 0 to 3 of the absolute value of v of t dt, which then turns into the integral from 0 to 3 of negative t squared plus 2t plus 3 dt. And then we're just using our antiderivatives again. So then we get negative t cubed over 3 plus 2t squared over 2. As you get used to this, the antiderivative of 2t is just t squared. And then the antiderivative of 3, we already said was 3t. And then I need to plug in 3 first, and then 0. So this gives me -9 again, plus 9, and then minus 0 plus 0 plus 0. And so then this just gives us 9. So we could do a graph to see maybe what is happening at t equals 0, and then t equal 1, t equal 2, and then t equal 3. That might give us some indication of if there was back and forth movement. But we don't even need to consider that. We can again just look at what's happening at the beginning, what's happening at the ending, and with these ideas of just integrating the function or its absolute value, we get the answers for the concepts of displacement and distance traveled.